Today, we are cracking the code on some of the most notoriously difficult problems in all of computer science. But what if I told you that deep down, they all share one incredibly powerful secret? Let's figure out what it is. Okay, so picture this. A traveling salesman trying to find the shortest possible route, a mathematician figuring out the absolute cheapest way to multiply a bunch of numbers, and a programmer trying to compare two different pieces of text. I mean, what could these three things possibly have in common? Well, the hidden link between them is a really brilliant strategy for solving what seems unsolvable. So first up, we have the legendary traveling salesperson problem. Imagine you've got a list of cities, and your job is to visit every single one of them exactly once, and then get back to where you started. The real challenge? Finding the absolute shortest path out of a truly mind-boggling number of options. Trying to check every single route, it becomes totally impossible really fast. Next on our list is something called matrix chain multiplication. Let's say you have a long sequence of matrices you need to multiply together. Turns out, the order you do it in, where you place the parentheses, massively changes how much work your computer has to do. The goal here is to find that one specific order that requires the absolute fewest calculations. And for our third puzzle, we have the longest common subsequence. Now, this one feels totally different, right? It's all about text. So given two strings, like exponential and polynomial, the question is, what's the longest string of letters that shows up in both of them, in the exact same order? In this case, it's ponial. How on earth do you find that efficiently? And here it is. This is the secret. The link between all these problems isn't about having a faster computer or just trying harder. It's about a clever trick. It's kind of like being lazy on purpose. It's the art of solving one small piece of the puzzle just once, and then remembering that answer so you never, ever have to calculate it again. This amazing technique actually has a name: dynamic programming. Now, I know, it sounds super complex, but the idea at its heart is just beautiful and simple. You take a huge, scary problem, and you smash it into smaller, overlapping subproblems. You solve the tiniest ones first, you store their solutions somewhere, and then you use those stored answers to build your way up to the solution for the original big problem. So the whole method really boils down to 4 key steps. 1, you divide the problem. 2, you solve the smallest, easiest pieces. 3, and this is the real magic here, you store that answer in a table. Programmers call this memoization. And 4, you just reuse those saved answers to build up to the final solution. Let's see how this actually works with our 3 cases. All right, first, let's go back to our traveling salesman. How in the world does he use this smart memory idea to find his way out of that maze of possible routes? Okay, the real key is how we store the information. Don't worry about the code on the screen for a second. Just imagine a giant table. Every single entry in this table stores the cheapest path we've found so far that has visited a specific set of cities and ends at one particular city. By filling out this table, we're building our solution piece by piece, always remembering the best possible path for every subset of cities we've already seen. This means we never have to recalculate routes we've already figured out. Now, I know that looks pretty intimidating, but believe it or not, this complexity is actually a huge win. A simple brute force approach would be what's called factorial time, which gets astronomically worse. So while this is still exponential, dynamic programming pulls the problem from the realm of literally impossible into actually solvable for a decent number of cities. And that's really the main idea here. For this explainer, we're really focusing on the strategy, the why it works, not getting lost in the weeds of the implementation. If you do want to see the code, though, it's all there for you in the comments. Okay, let's move on to case number 2. How do we find the cheapest path, not through a map of cities, but through a long chain of math calculations? So here's the core logic. To find the cheapest way to multiply a long chain of matrices, we basically test every possible place we could split that chain into 2 smaller pieces. And for each of those potential splits, we don't have to recalculate the cost of the 2 smaller chains. Nope, we just look up their already solved minimum costs in our table and add them up. It's this beautiful recursive idea that's powered by our smart memory. And what's the result of all that? A time complexity of O of n cubed. Now, in the world of computer science, that is a fantastic improvement over a brute force approach that would be exponential. This makes the problem totally practical to solve, even for really long chains of matrices. See, it's this pattern of building on top of answers you've already found that unlocks such a massive gain in efficiency. And again, if you want to see exactly how this translates to code, the full C++ implementation is linked right down in the comments.
All right, time for our final case. Let's see how this powerful memory trick can be used for something that feels completely different, finding hidden patterns in text data. The way this works is by essentially creating a grid. We compare our two strings, character by character. If the characters we're looking at match, the answer for that spot in our grid is just 1 plus the answer from the previous spot. Simple. If they don't match, we just carry forward the best answer we had found right before that. By filling out the grid this way, we systematically build our way to the final answer. And this approach gives us a super efficient time complexity of O of m times n, where m and n are just the lengths of the two strings. This is incredibly fast, and it's the reason why algorithms just like this are used in everything from the spell checker in your phone to DNA sequence analysis. It's an elegant solution that scales beautifully, whether you're working with simple words or incredibly complex biological data. And you guessed it, if you want to dive deeper, the full C++ solution is waiting for you in the comments. So, from routes on a map to numbers to text, we've seen the exact same powerful strategy pop up again and again. It's not about the specific problem, it's all about the approach. It's truly the power of smart memory. So, what's the big takeaway here? Well, it's this simple but incredibly powerful pattern. Break down a huge problem into smaller, manageable pieces. Solve each of those small pieces exactly one time. Store those answers systematically, and then reuse those answers to efficiently solve the original problem. This simple pattern of remembering is what turns impossible problems into solvable ones. And that kind of leaves us with one final thought. Now that you know the secret sauce, this core idea behind dynamic programming, where else could it apply? What other complex problems out there, maybe in coding or even in life, are just a collection of smaller puzzles waiting for someone to apply the right kind of memory? If you do want to dive deeper into the how and see the code we talked about, you'll find links to all the implementations in the comments below. Thanks so much for joining me.